Okay, so a reminder that you have a couple of homework assignments that are due tomorrow. One is vocabulary for chapter 6 and one is the prepare to learn for chapter 6. So both of those are found on Canvas. I didn't split up the prepare to learn for chapter 6, so this is the only one. So this means after this one, you don't have any more. But it does cover the whole chapter rather than just focusing in on the beginning part of the chapter. So just kind of be aware of that. I will be assigning homework 20, which will cover the light stuff that we're dealing with, and that will be due at the end of Thanksgiving break. So any questions? Okay, so we are going to be jumping into chapter 6 and into light. So first you might be wondering why we're dealing with light when this is a chemistry class. And chapter 6 deals a lot with the atomic structure. We've talked at the beginning of the semester about protons and neutrons in the nucleus. Now we're going to be focusing on the electronic or electron portion of that. And so I'm going to do a brief overview of atomic structure that we've gone through so far. You don't need to write that stuff down. That's just kind of a reminder of what we talked about in the past. So you'll see the connection between what we're trying to get at and the light that we're going to be talking about today. So for light, we have a few objectives for today. We want to verify that light is a wave. So we want to have evidence for the wave nature of light. We'll talk on Friday about how light also has a particle nature to it. And so if it is a wave, then it has certain properties we want to be able to talk about: the frequency, the amplitude, and the wavelength. The wavelength and frequency are the more important of those. And then we want to be able to calculate the conversion between the wavelength and the frequency. So we'll go through a couple of examples. We'll get to, hopefully, fingers crossed, the different types of electromagnetic radiation. We won't have time to talk about how they interact with matter, so that will have to be on Friday. So this is kind of the overview of what we're going to be talking about today. But as I said, we're going to start off talking about reminding ourselves of what we know about the structure of the atom so we can see where we're getting into light. And so you might remember that Dalton, 200 years ago, had the idea that an atom was basically this hard sphere that was the same throughout. You couldn't break it up into smaller pieces. There were no different parts to it. And then in another 50 years or so, actually it was the end of the century, so it was like almost 100 years, Thomson came along and did his cathode ray tube experiment. And in that experiment, he was able to show that there is something small and negative that's part of all of these atoms. And so therefore, we have this idea that, okay, atoms have these little negative particles called electrons in them. At the time, the idea was that the rest of the atom was just some sort of solid or putty-like mass that had these electrons embedded into it. We call this the plum pudding model. And it took only 15, 20 years before Rutherford came up with his nuclear model with the help of his graduate student Geiger. They showed that the nucleus had all of the positive charge in a very, very small space. And so with this picture, it looks small, but not teeny tiny. If this were actual relative sizes, that would be too small to see. We wouldn't be able to see the nucleus in an atom of that size. So it's a very, very tiny space. And then we just kind of left it off at that point. What we want to get to is what is going on with the electrons. That's what we call electronic structure. And this model kind of begs the question that if we have all of these negative particles on the outside and we've got this positive charge in the middle, why don't those electrons go crashing into the middle? And so the model right now is kind of, well, the electrons are just kind of willy-nilly going anywhere that they can. They're just moving around everywhere. But in order to answer this question, we use an analogy to another attractive force. So positives and negatives are attracted to each other. So electrostatics is an attractive force. Another attractive force is gravity. So we might take an object like the Earth and an object like the moon. So things that are attracted to the Earth generally just fall to the Earth, but the moon is a really big, heavy object. It's attracted to the Earth, but it hasn't crashed into the Earth yet. Why not? And so the reason for that is because it's orbiting. And so the idea for the electrons is, well, what if they are actually on these orbital rings? It's not a physical object, but they're on a path and they're circling around the nucleus. They're also orbiting. So we might have a path that looks something like this. All right. And I'm going to skip over that question. Okay, so let's talk about why orbiting actually works. So this picture here is my crude artist rendition of the Earth. Zoomed in really close, so we know the Earth has a curved surface. So this is just a portion of it. And then there's a ball, and it's being held by an invisible person, so it's in the air. And it's going to change colors here. Okay. Now, if this invisible person just lets go of that ball, we know what's going to happen. It's going to fall straight down to the Earth. So that's what we expect when there's no orbiting at all. But we also know that if this invisible person is on a baseball team and they're the pitcher, then they might be able to throw this ball sideways. Now, if it goes sideways, if you throw it sideways, it doesn't just leave your hand and then fall straight down. It takes a curved path or trajectory, okay? So if I have initially some sideways motion, it's going to start falling and it'll gradually go down. Now, it's not going to go in a straight line. It's going to be a curved path, but it's going to go down after a distance. So let's imagine we've got some super strong, maybe it's the Incredible Hulk throwing this baseball, and they can throw it hard enough and they can throw it fast enough that when they throw it, it goes sideways so far that by the time it has dropped down to the level where it would have hit the ground, the Earth is curved away from it. Okay, so here's this sideways and it just missed the Earth. So this is a ball that's falling towards the Earth, but by the time it gets to the place where it should hit the Earth is curved away from it. And so it keeps falling towards that side of the Earth, but the Earth keeps curving. That's kind of how orbiting works, is that the moon circling around us is constantly falling towards the Earth, but the Earth is curving away from where the moon is, or, you know, moving out of the way before the moon can crash into it. Okay, so we're going to assume that electrons are kind of working on that principle. Okay, so we build what is called the solar system model of the atom. This is a lot of times what gets taught in like elementary and middle school, because little kids have a hard time picturing things that they can't actually put their hands on and can't see. They can't abstract very well. There are a lot of problems with this model, but it is good for kind of understanding the basic idea of how the atom works. So this is Bohr's atomic view, and we'll get back to Bohr later. But his idea was that each electron has a pathway that it is on, and that when you have energy coming in, like light, it can actually move the electron from one pathway to the other. So we know that, say, Mercury goes around the sun on one path, and then Venus on a larger path, and then Earth on an even larger path. So the analogy here would be if a bunch of energy came in and hit Mercury and it moved out to Venus's path, okay? And so that energy could come in the form of light. So we absorb light and the electron moves out further away from the nucleus. But because it's negative and the nucleus is positive, eventually it's going to relax and go back to its original position. When that happens, it's been observed that light gets emitted. So here I say energy is released, but we can think of that as being light. Okay, energy is emitted in the form of light. And so that light is telling us something about what's going on with the electrons in the atom. And so that's why we need to study light, is so we can understand how we can talk about light, measure light, so we know what we're talking about when we describe what's happening with the atom. Okay, so let's talk about light. Newton is quite revered in the scientific circles, especially in physics. And in the 1600s, he pretty well assured everybody that light is a wave. And there's lots of good evidence for that. But in the 20th century, there was a lot of work in trying to discover the structure of the atom that said maybe light is a particle. And so there was a debate over that. Today, we're going to focus in on just light being a wave. Friday, we will look more at it being a particle. So why does it matter? Because light waves are continuous. If you think about it like an ocean wave going up and down and up and down, there's not really a start to one wave and an end to the next wave. It's all continuous. Whereas if I have a particle, like a baseball, there's a place where the baseball is and a place where the baseball is not. So it is not continuous. So we say it is quantized or discrete. So we'll come back to those concepts again on Friday. Okay, so the next couple of slides are kind of hard to see, so I'm going to turn out the overhead light. So first we need some vocabulary to describe what a wave is, like how big is it, how fast is it moving. And so one of the things that we have on here, we have two different waves. So one is going way up and down, and one is just going a little bit up and down. They're both in red. If we look at, on the left-hand side, there is an arrow pointing from the midline to the top. The top of a wave is called its peak. That distance from the midline to the peak, or from the midline to the very bottom, which is called the trough, that is called the amplitude of the wave. So that's how we measure how tall a wave is. And so we can see this one on the left is measuring a very large amplitude, and then more towards the right, we're measuring the smaller wave. It has a smaller amplitude. So the amplitude is the height of the wave, and it tells us the intensity. In some ways, that's related to the energy of a wave. So if we think about an ocean wave, a 10-foot tall ocean wave is going to have more destructive power running into buildings or moving around boats than a wave that's just maybe a foot tall. Okay, so the higher the wave, the more power it's going to have. Now we're going to find that for light, we have other ways of measuring its energy. So we're not going to deal with amplitude too much. The other two properties are a little more important. So wavelength. Now we have some specific symbols that we use. This one kind of looks like an upside down Y. That is the Greek letter lambda, and it's for the letter L. And L stands for length. So its wavelength is lambda. So the wavelength can be measured going from one part of a wave to the same part of the next wave. So the way they're showing it on here is the very bottommost part of the wave is the trough. They're going from the trough of the first wave to the trough of the next wave. That distance is the wavelength. Now that should be the same distance if we went and said the peak of one wave to the peak of the next. So those are usually the two ways to measure it the best. If we pick other portions, we're going to find that there's an up and a down kind of hitting the same location. So like if I take where it crosses this midline, the next time it crosses the midline, it's going up instead of down, and that's only half the wavelength. So I need to go all the way over here to get the full wavelength. So usually we just measure at the peaks. All right. We're going to find that for light, the wavelength will also tell us the color of the wave. The other thing we're going to measure about waves, because waves are moving, is their frequency. So the frequency is represented by this letter here. It looks like a V, and if you want to think V in your head, that's fine. But what I will say is it's nu. That's also a Greek letter. It is the Greek letter N. So when I say you're going to solve for something, I might say, oh, you're going to solve for nu. But that you can think to yourself, that's the V. So frequencies is cycles per second, but it is also, when we say cycles, we mean how many times does it go up and down, go all the way through its motion in 1 second. So if this box represented 1 second, then this wave would have 2 cycles per second. Okay, so it can be measured as per seconds, or it can be measured with a unit of hertz, and we'll see that in a little bit. The frequency is very strongly tied to the energy. It's not exactly the same thing as the energy, but they kind of work in tandem together. So we'll see on Friday how that works. So we said we wanted to be able to convert between the wavelength and the frequency. We are going to need the speed in order to do that. And it turns out that for light, that speed is pretty consistent. Okay. So it's a constant. I will always provide it to you. You don't need to memorize it. And so we end up with the formula C equals lambda nu. All right, so if I wanted to calculate the speed of light, I would take the wavelength of a wave and the frequency of the wave, multiply those together, and I would get the speed of light. Now, I did say that the, yeah, Glenn.
So when you have intensities and frequencies, does that mean
Amplitude is measuring intensity.
like how bright the light is?
Yes. Okay, so we also said that C, or the speed of light, is a constant, so it's not really changing a whole lot. So we're very rarely going to be solving for C. We're usually solving for either frequency or wavelength. So, let's see. I think if I do that, yeah, that's there. Okay. Okay, so if we look at this description of the equation I just gave you, C on top of lambda nu, anytime we're looking for one of these, we can just cover it up. So if I'm looking for the frequency, this V looking thing, I cover that up and I end up with C over lambda. If I'm looking for wavelength, I cover up wavelength and I get C over frequency. So C, the speed of light, is always on top. Okay, so hopefully that will help you in these calculations, is anytime you're using C, just keep it on the top of the fraction. All right, so if we solve for frequency, we end up with frequency is C over lambda. And we're going to use that calculation here in a second. All right, so I have some baskets out in front of you. And in those baskets, you should have a cardboard box that has some different lights in it of different colors. They kind of look like this. And what I want you to do is pull out the red one, the purple one, and then either the yellow or the green one. And then you're going to find a piece of paper. It's almost rubbery, not paper-like, that looks like this. It's white on one side and yellow on the other. This is phosphorescent paper, so I'm going to turn out the light here so you can see the glow. That's on. Here's off. All right. So what I want you to do is take the red light first. You just squeeze it to make it glow and kind of hold it close to the phosphorescent paper and see if you can get that to glow with the red light?
Which side?
The yellow side. All right, and after you've observed that, then try it with the other colors. So you should notice that with the red light, not much happens, right? There, you maybe don't even notice any glowing at all. With the green or yellow, you might notice a faint glowing. And with the blue or the purple, you should get a pretty bright glow. It should be very visible. Is that about what you're noticing? All right, so different colors of light have different energy. We talked about our connection to the atom was that the light was making the electron move away from the nucleus. Okay, it has to make the phosphorescent paper glow, it has to give it enough energy to go to the next level, because if it can't go to the next level, it's just going to go back home and stay where it was. So the red light doesn't really have enough energy in this paper to move the electron away to make the glowing happen. As we move across the rainbow spectrum from red to green to purple, then we start getting higher and higher energy. Okay, so red is low energy, purple is high energy, and then they go in order of the rainbow across from there. All right, so if we look at these waves here, we have red, yellow, and blue. Now, the frequencies of light are much greater than what is shown here, but this does show relative to one another how it works. So you'll see the red at the top has a longer wavelength. Okay, so it says wavelength A, and then it's narrower for the yellow and even smaller for the blue. Okay, so we have wavelength decreasing as we go from red to blue. Okay, now remember we said that this side to side kind of represents 1 second. And so we could see the frequency by how many full waves, how many peaks we can get going across there. So the red, we've got 3 definite peaks, and we kind of got on the ends halves of another peak. So we've got about 4 peaks for the red. So a frequency of 4 cycles per second. But with the yellow, it's 8 cycles per second. And with the blue, it is 16 cycles per second. Okay, so the blue has a smaller wavelength, but a higher frequency. So what that tells us is they are inversely proportional, just like pressure and volume. As one of them goes up, the other one goes down. All right, and then these are related to energy, because the higher the frequency, the higher the energy. And so you might think about if you were trying to represent these waves with a motion of your hand, the red one is kind of a lazy up and down, bobbing along on the beautiful briny sea. And if we go to the blue one, I mean, it almost looks like it's really tense because it's going way up and down, right? Much more energy is required to get that really fast frequency for the blue, okay? So all of that put together gives us that radiant energy, all of the kinds of light that we're talking about travel at the same speed, c. Okay. And we can look at energy, frequency, and wavelength and relate them to one another. So if we have something that is high frequency, it is also going to be high energy. All right. And so our rainbow here goes from low frequency to high frequency. So red is low energy and purple is high energy. And oppositely, long wavelengths gives us low energy. So the red was the low energy. You might not be able to see these numbers here. But way out at the end of red, it says 750 is the wavelength. But the wavelength for the purple is 400. Okay, so it's a little more than half of what the wavelength is for the red. Okay, so we want to keep those relationships in mind. All right, so the next thing that we're going to do is we're going to look at some calculations. So you might want to pull out your calculator. Anybody still need this slide? Okay, so let's say we have a red laser pointer and it has a wavelength of 650 nanometers, and we want to know what that frequency is. Okay, so we're going to use, covering up the frequency that we're looking for, C divided by lambda. And then I have C written on the board here, but C is 2.998 times 10 to the 9th, 10 to the 8th. Sorry, there's a 9 in there somewhere. Okay, so that's C. Now we have 650 nanometers. A nanometer is 1 times 10 to the -9th meters. It's very, very tiny. So it is 1/1,000,000th of a millimeter. Millimeter is about as wide as your hair. You could take a hair and divide it into 1,000,000 equal-sized pieces. That's about how big a nanometer is, okay? So we're gonna wanna represent this with scientific notation. So what we're gonna do is we're gonna take our 650 and we're gonna multiply it by 10 to the -9. Now I wanna take a second to look at a calculator, and I promise I'll come back to this slide. But I wanna show you on your calculator, because this is the first time we've really needed to use the scientific notation. All right, so if I type in 650 times 10, then this x to the y is my to the, then I can't put in the negative right away. I have to put in the 9 first, and then there's this plus minus button. So that's kind of confusing. You're not going to use the subtract button. You're going to use the plus minus button. Now, when I do that, notice that I don't get times 10 to the on the display. I've got 6.5, and then I've got a little exponent there that says -7. Okay, so when I moved the decimal over from 650 to 6.5, I had to change that exponent. But the way it is displayed on your calculator, they don't write out the times 10 to them. So you got to get used to, like when I'm looking at that, I have to mentally stick in times 10 to them. Okay. There is another way to do this, and it can be very helpful for making sure that you get the fractions done correctly. So the way you would do that is you would do 650, and then this button that says EXP, or if you have a graphing calculator, it's usually 2 capital letters EE. So I push that button, and then it gives me the place for the exponent there. And then I put in my 9 negative. Okay, so I got the same thing when I plugged it in that way. You can do one of those, either times 10 to the or exponent, but don't do both. So let's see what happens if I try to do both. 650 times exponent 9 negative. That's a completely different number, okay? So you can either do times 10 to the, or you can use the exponent button. Don't try to do both. That's one of the common mistakes. All right, so we're going to practice and look at what the calculation is. I would recommend that if you have your calculator with you, try plugging that in and make sure you get the same number. Make sure you're plugging it in properly. Now, a good rule of thumb for doing these calculations is that for most frequencies, especially visible light, ultraviolet light, infrared light, you're going to end up with something that is times 10 to the 14th. You might get times 10 to the 15th. So if you're plugging things in and you get something that's not times 10 to the 14th, go back and check your calculations. Make sure you plugged in things properly. All right, so we're going to try another one. The next one's going to be green light. Yeah.
Hertz just equals 1/2.
Yes, sorry, I didn't say that. So hertz is the unit for frequency, and it's the same thing as saying 1/seconds, so that you don't have to say 4.6 times 10 to the 14th per seconds. That just sounds weird. So we came up with a unit for it. All right, so the red light is 650. The green light should be what? A bigger number or a smaller number? So this is wavelength. It is a higher energy, which means that a smaller wavelength. So it is 520. All right. So take a second to try and plug this in. Then by show of fingers, with 1 being A and D being 4, which of these do you think is the correct answer? Yep. Yes. Yes. Okay. So if you remembered my saying on the last slide that these are usually going to be 10 to the 14th, that's a good way to kind of eliminate some choices. So this is the only one that's close to that, but hopefully you plugged it into your calculator. You actually got that number and didn't have to just guess. All right, we're going to talk about the properties of light on Friday because I'm just really slow in the afternoon, I guess. But before we go, I